Hello everyone. So today's topic is rotational motion. We're going to talk about a new unit called radians, which is used to measure the angle, but it's a little different from degrees, the unit that we've been using all this time. Radians is a more geometric, math-friendly kind of unit. It's widely used in math and physics. And we will talk about rotational quantities. So similar to linear quantities like distance, velocity, acceleration, when things are rotating, we can define the same kind of quantities in the rotational motion. For an example, if something moves in a straight line, in one direction, you call it the distance or displacement. If you measure some distance along the length of along the perimeter of a rotating object, or if you measure the rotating velocity or the rotational acceleration, so for every linear kinematic quantity there's a rotational counterpart. So we're going to talk about that. And then using all these, we will talk about rotational kinematics, a set of kinematic equations specifically for rotations. Since you already know these kinematic equations, this will be pretty easy. They all have the same format. And then we will work on few examples. Okay, so rotations are pretty common in nature. Whenever we study motion, it is a big part of motion. Like if something moves in one direction in a straight line, or if the whole object is moving, we call it translational motion. So all these examples we did, like pushing a box across the floor or a vehicle moving along the road, the whole object, everything, entire object is going in the same direction, so that and has the same speed. That's translational motion. If something is rotating around a fixed axis, that is called rotational motion. So sometimes things can have both, a combination, like if something is moving while rotating, that's rotational plus translational motion, right? So we'll talk about these things in little detail. But we need to talk about first this radians, measuring angle. What is radians? So let's talk about radians first. Okay. So what is radians? I'm going to explain this to you using an example. Radians. Let's say we have a full circle. It's a very bad looking circle, but still you get the idea. And you know that if you start from one point like this and if you go around it, the total angle you cover in degrees is 360. Right? One full circle is 360 degrees. Or if you go half a circle like this, we say that 180. We put a little circle next to the number to indicate that it's in degrees. Let's say the radius is r. Now if you want to find the perimeter or the circumference of this circle, we say that c equals 2 pi r. The circumference is 2 pi r, right? The length measured around the edge of the thing. Now where is this 2 pi coming from? What is this number? 2 times pi stands for 3.14 approximately, right? So that's in geometry we can say regardless of what's the radius, if you multiply the radius of a circle by this particular number, you get the length of, or the circumference, the length measured along the perimeter. Now if I divide C by R, I get 2 pi. Again, what is the speciality about this 2 pi term? What I'm doing here is I'm dividing this circumference by the radius. Over here, if you go around half the circle, now a full circle is 2 pi. In that way, half a circle should be pi. So if I divide this length, half of that, whatever that length is, divide by that radius, I get just pi. Or if I have like here's a circle and with radius r, I take some length like this piece, we call this an arc length. I divide this length by this radius, I get this portion, like over here, when you divide the entire circumference by the radius, I get this entire angle covered, right? When I divide this half of the circumference by radius, I get this half of that 360, which is 180 portion covered. When I divide this length by the radius, I get whatever the angle inside that. So this angle over here, theta, when you divide an arc length by the radius, we get an angle that is the angle given in radians. That's the idea of radians. When you divide an arc length by the radius, you get that angle, whatever that angle covered in that portion, in the units of radians, right? So how big is a radians? When you go the full circle, 360 degrees, we say that it is equals to 2 pi in radians. So that means a pi in radians, we say rad in shortened form, is equals to 180 degrees. So what is 1 rad? 1 radians. How big is a 1 radian unit? It is 180 divided by pi, and we know that pi is 3.14 approximately. 180 divided by 3.14. So I take the calculator, plug the numbers, it's a little less than 60. 180 divided by pi, 57.29 degrees. So 1 radian is a large, compared to degrees, it's a big unit, right? So 1 radian is about this big, I would say, 57.3 approximately degrees. This many degrees is equals to approximately 1 radian. So compared to that, what is the size of a 1 degree? 1 degree is about this much, right? Really small. You see, a radian is approximately 60 times bigger than a degree. So radian is a big unit. And now you get the idea. This is where this 2 pi coming from. You want to find the length of the full circle, the entire circumference, you multiply the radius by that angle in radians. So we don't have to say 2 pi all the time. It's same as saying circumference equals 2 times 3.14 3.14 times radius. That means the same thing, right? So we just give this a letter symbol pi to indicate this specific number 3.14. So we'll work on few examples so that this idea will get you'll get more comfortable with the idea. Okay, so let's do a few unit conversions. Let's see, how do we go back and forth between degrees and radians? Let's say we have now we know that 360 degrees is 2 pi radians. 180 degrees is pi radians. Or you can now, since pi stands for 3.14, you can say it's 3.14 radians. What about 90 degrees? 90 degrees will be half of that. You can either divide this by half and say 1.57 or something, or you can just say pi by 2 radians, right? Whatever it is, 3.14 divided by 2. 45 degrees, these are widely used angles, 5 by 4 radians. Lastly, 30 degrees. What is 30? If 180 is pi, 30 is 180 divided by 6. So therefore, pi divided by 6 radians. So this way. These are some of the widely used angles that we convert into radius. What about something like 50 degrees? You can't directly, I mean you can, but it's not that easy as these above examples, so we have to do some math first. There's your calculator can directly convert it. If not, let's try this way. So we can always start with a known number, so something like this. Let's try this. 180 equals pi radians. This is something we should remember all the time. This is our starting point. If you know this, you can find any other angle. So if 180 is this, what is 1 degree? 1 degree divided by pi divided by 180 radians, right? So now we know what is 1 degree is. This is same as saying 3.14 over 180 radians. Or you can say, let's divide it and see what is 1 degree. 3.14 divided by 180 equals 0.0174 radians. That's how big is a radian. 1 degree is a small fraction of a radian, right? So this is the radian amount. So what about 50 degrees? 50 degrees will be 0.0174 multiplied by 50 radians. Or in other words, it will be close to 1 radian. So multiplied by 50, it's 0.87 radians. It's not a full 1 radian, but close. Okay, so here we convert a degree value to a radian value, right? So let's try going the other way. How about I'm trying to write 2 radians. How many degrees? So how do you go the other way? You can always remember pi radians equals 180 degrees. So 1 radian equals 180 over pi, or 180 over 3.14. Pi is just a symbol for 3.14. It's not 3.14. It doesn't end there. It never ends. There's so many decimal points. there's the whole math behind it, like how many decimal points are there, but for us, we can shorten it and just keep 2 decimal points. That's more than enough. So this is 1 radian. Again, we know that we did this math some time ago. As I remember, it's 57 point something. Let's try that real quick. 180 divided by 3. Let me try 180 divided by pi is 57.3, 57.29. So 57.29, that is 1 radian. So what is 2 radians? 2 times that, 57.29 multiplied by 2, close to 120, multiplied by 2 gives you 114.6 degrees. 2 radians is this many degrees. So you can go back and forth between radians and degrees. You should be able to do that. My recommendation is remember this or remember this. 360 is 2 pi radians or 180 is pi radians. When you know that, you can manipulate it and find whatever other angles you want. Okay, so this is how you go back and forth between radians and degrees. Alright, so let's move on to a new topic. Okay, so earlier I told you about this arc length concept. Well, you don't have to have a full circle. Let's say you have a piece of a circle. So here's the center. Here you make some angle, and this is part of a circle. So the rest of the circle goes like this. So we are interested in this part, and here's the angle theta. Now it's important to know that we're going to measure the angles in radians from now on for most of these calculations, right? So this angle looks like 20 degrees to you, but it's a fraction of a radians. So keep that in mind. And the radius is here. The arc length, the length, oops, not good. The length measured along this line is L. And the relationship is, if you divide this L by R, you get theta in radians. R could be a couple of centimeters, L could be a couple of centimeters. You divide one by the other, you get theta in radians. So for an example, let's say R is 10 centimeters and this length is 5 centimeters. So what is the angle in radians? L over R is theta. 5 centimeters over 10 cm, which is centimeters goes away, 5 over 10 is 0.5 radians. That's theta. Theta is half a radians, right? We know that radians is about 57.3 degrees, so it will be half of that, so 25, it's like 28 degrees or something like that. Alright. What if we have same circle, right? This is 10 centimeters. What if we have a piece of arc length making let's say 90 degrees here? What's the length? So how do you find that? Length is r theta. R is 10. So we're going to go with centimeters. Now theta, you can't put 90 degrees. You can't put degrees. You have to put the radians equivalents. 90 is pi by 2. So what is L? This will be, cancels out, gives you 5. Phi, pi. What is 5 times pi? 5 times 3.14. And which is 5 times pi is 15.7. if this is 10 centimeters, if it is making a 90-degree angle, this arc length will be 15.57. What will be the length of the entire circle? This is 1/4 of it, right? 90 degrees means 1/4 of it. There's another 90 here, another 90 here, another 90 here. So the total length or circumference, it will be 15.7 times 4, which is equals to 62.83 centimeters. But we know that circumference can be found this way, 2 pi r. This is what I'm trying to show you. Where is this 2 pi coming from? So let's plug the numbers. 2 times pi times 10 centimeters. 2 times pi times 10 centimeters gives you the same exact number, 62.83 centimeters. Okay. All right. Moving on. Let me erase this whole thing and start a new page. So now we all know that we have this equation L equals R theta. This is our starting point. Theta is an angle measured. L is a length measured along the arc. This radius of the circle is what connect one to the other, right? An angle and a length are connected by the radius. So in this circle, the radius is r, and let's say this is our theta, and this is where the length is. This arc length is connected to this angle by the radius. So radius is actually the connecting factor in many rotational equations. Radius is super important because of that. Okay, so let's say there is some dot here which is moving in a constant speed going along this thing, right? It goes like this. Let's say this dot moves from this point initial to this point here, final, in a time interval of, so it goes from initial to final in t seconds. So here the angle changed. So so it was initially here, then finally initially you can say theta was 0, right? Initially it was here. Now finally the angle became this whatever theta we have, so finally theta is just theta, right? So the change in angle, we have a change in angle, it goes from here to here. So actually I didn't explain it well, so let me draw this again. It will make more sense to you. When I do this, it was initially here, now it's here. The change in angle is delta theta. The angle changed in a time interval of t. The rate of change of angle, the angle divided by time, is defined as angular speed or angular velocity, omega. This W looking letter is called omega, and it is the rate of change of the angle, or how fast the angle is changing. In other words, how fast something is rotating. This is kind of the counterpart to the velocity, right? This is angular velocity. Omega is angular velocity which is angle divided by time, so the unit is radians per second. Okay, all right. So let's go back to our equation. We have L equals R theta. So when this thing rotates, or when this dot moving from one place to the other, oh, I'm making a mess here, so let's go back to this one here. When it is moving from the starting point to the next point, the length is changing. So we have a velocity moving this way. Length divided by time gives you velocity, right? So what if I divide this equation both sides by time? This time, this side also time. The left hand side, it's a distance. Even though it's not a straight line, it's still a distance divided by a time. So it's a speed. We can say it's a velocity with changing direction. Over here, I can leave this r as it is. Then I have theta divided by t, and I know that theta divided by time is same as delta theta, angle change divided by time, which is omega. So here we have angular velocity. Now you see the linear velocity, or the velocity measured along the edge, is connected to the angular velocity by radius. That's why I told you radius is super important. It connects rotating things into translational things. Now if this thing is speeding up, let's say while moving it increases the rotational speed, omega is changing. It's not constant, but it's changing. So for an example, initially omega was omega initial, now it's omega final. It increased, means the rotating speed increased. So now we have a delta omega. So if I divide delta omega by time, what do I get? Alpha. This is called angular acceleration. Angular acceleration units are, omega is already radians per second. We divide it again by second. We get radians per second squared. That's angular acceleration measured in alpha. This tells you how fast the angular speed is changing. Now let's go back to this equation over here. What if I divide both sides by time? V over t equals r omega over t. We know that a linear velocity divided by time gives us acceleration. Over here, r omega divided by time, alpha, angular acceleration. Here we have another equation where linear acceleration connected to angular acceleration by the radius. So we have this equation, we have this equation, and we have this equation. They all shows you how linear things connected to angular things through the radius. Okay, so these are three important equations. All right. So before I erase this, I want calculus class to know, if you are in 230, physics 2030, these things are defined. Omega is defined as, you already know this, d theta by dt, right, the derivative of angle, and angular acceleration is defined as d omega by dt, or you can say dt d squared over dt squared, the second derivative. All right. Okay, so let's try some examples. All right, so let's say we have an example where there's a spinning disc. So here's the disc. It can be like a horizontal surface like this, here's a disc which spins around this axis, so I'm just gonna draw it this way. So let's say this disk has a radius of 0.5 meters and it's spinning at a constant speed or a constant rotational speed, and it makes one full cycle every let's say 5 seconds. So the question is, what is omega, or angular speed? So how do you find omega? We know that omega is the angle theta or delta theta divided by time. So it says it makes one full cycle every 5 seconds. Now remember, omega has to be in radians per second. So the whatever the angle should go in radians. It makes one full cycle. So what is a full cycle? It's 360 degrees or 2 pi radians, right? So this is what we need to plug in. So 2 pi radians in 5 seconds. So use the calculator. You can either type in 2 times 3.14, or calculator has the pi sign, you can use that. So 2 times pi divided by 5 gives you 1.256 radians per second. That's the omega value. Sometimes in some books they leave the answer as it is 2 pi over 5 radians per second. That's fine, but I prefer you do take the next step and get rid of this pi and have a like a number answer. Mostly in my exams it will be asking for this. Okay, alright, so that's a simple example. Let's try another one. Alright, so second example. This time let's say we have a merry-go-round. Right, in carnivals kind of places you see these things, merry-go-round. So it is rotating around this axis. Let's say there's a child sitting 1.5 meters from the, or let's say 2 meters from the rotating axis. Now the merry-go-round starts from 0 and it accelerates, right? It speeds up. So let's say initially it was at rest, and then let's say 20 seconds later omega became 0.2 radians per second. So it's speeding up. It reached some omega after 20 seconds. Let me make it 0.3. Okay. Question is, for an example, what's the acceleration? What's the angular acceleration? Alright, we know that acceleration is delta omega divided by time. So delta omega is omega final minus omega initial over time. Omega final after 20 seconds it reached 0.3. Initially it was 0. All these things took 20 seconds. So our alpha is 0.3 over 20. 0.3 over 20, which is 0.415 radians per second square. I can ask another question. After 20 seconds, what's the linear speed of the child? So after 20 seconds, what is the speed or velocity? Now omega, the angular velocity, we already know it's given 0.3. What about the linear velocity? V, which is r omega. So 2 times 0.3, which is 0.6 meters per second. So at that point, sometime later, child is over here, right? It rotated. So let's say he's over here. He's going at 0.6 meters per second. Like the moment, at that moment, his linear velocity along the edge of the circle is 0.6 meters per second. Another interesting thing about rotations, it's not relevant to this problem, but if you think about it, so let's say here we have a circle with some radius. If you think about 2 points along this line, when the circle rotates to this point, this guy is over here, this guy is over here. They both rotate at the same angle theta, right? Angle is common, but the linear distances they travel, this is shorter, this is a longer distance. If we call this A and B, the length that B traveled along the edge is bigger than the length that A traveled. So one thing to remember, they will both rotate the same angle theta. As a matter of fact, every point anywhere on this circle will rotate the same amount of theta, but also they will all have the same theta. They will all have the same angular velocity as well. They will all have the same omega. But the linear distances, the L they travel, their velocities, V, these are different, right? This length is shorter, this length is bigger. And as a result, this side will have a bigger V, this guy will have a small v. Their speeds are also different. Okay. Alright, moving on. Okay, so let's clear this. So finally, I want to mention that in kinematics, we solve a lot of different problems, vehicle moving, accelerating, we calculate how far they go, how much time it takes, what's the final speed. We can do all these things in rotations. Let's say we have a disk rotating around a fixed axis. Every time, whenever something's rotating, we have to define, one thing we have to define is where the axis is and preferably what the radius. It doesn't need to be a disk, it could be some point goes in a circular path. Still you have to say what is the radius, where's the axis, and all those information. So we can calculate things like how far, what is the angle it rotated at a given time, what's the starting angular velocity, what's the final angular velocity, what's the angular acceleration, what's the angle it rotated, theta, all those things. So in kinematics, we have this set of equations that you are familiar with. V final is equals to V initial plus AT. We have V final squared equals V initial squared plus 2ax. Then we have x equals V initial t plus half AT squared. All these have rotational counterparts. V final, omega final, acceleration alpha, angular acceleration, omega final squared, omega initial squared plus 2 times alpha times distance. What's the rotational counterpart for distance? This is distance, this will be theta. X is theta. Omega initial times plus half times alpha t squared. You see, time is going to be common in both the equations. So these are the rotational counterparts or rotational kinematic equations in motion. So this is also very, very important. All right, so I can give you an example problem to work with. Let's see. Well, I'll discuss the examples in class. All right. Okay, thanks.